collection offers us a powerful tool to do this. So to look at an example of how this works, I'm going to start with slides. Yes, great point. Okay, sorry about the technical snafu. Okay, so let's see an example of how this works. We're going to reanalyze the same simulated data that we worked with yesterday, except now we're going to try to fit the signal that's in the data with a sinusoidal function instead of a linear function. And then we're going to try to compare to see which gives us the better fit. So in addition to our linear model that should look familiar, we're going to define a new model that is just a sine function, and there are going to be two free parameters. There's going to be an offset in both the sine model and the line model, except the sine model is also going to have this angular frequency parameter related to the period of the data. Okay, so if we take a look at our data again, the blue points are the data, the red is the true signal that we have added to our data, but now we're going to fit it with something that looks like the green signal because we're going to pretend we don't know that the true signal is actually the red signal. Okay, so how can we use Bayesian inference to quantify what kind of model is going to give us a better fit? We can calculate something called the Bayes factor. And I have introduced this fancy Z notation for the evidence, but really when I write Z sub A or sub B or whatever hypothesis, this is just the evidence for the data given that hypothesis. It's just a little more notationally convenient, but it is the same evidence that we introduced yesterday. And so the standard lore, because it's somewhat arbitrary, is that if you get a natural log Bayes factor greater than 8 for one model over another model, that is significant statistical evidence that the one model is preferred over the other model. So, Bayes factors in the range of, or log Bayes factors in the range of a couple are not usually considered strong statistical evidence in favor of one model or another. So yesterday, when we analyzed the same exact data set with a linear model, we calculated a log evidence of minus 151.78. The exact number doesn't really matter until when we're actually going to go back and calculate the Bayes factor between the line model and the sine model. So now we're just going to go through and calculate again on a grid this time. So we're not using the very, very helpful stochastic sampling techniques we have just explored. We're just going to do it on a grid because we only have two free parameters. And so we're going to set up our priors on our angular frequency and offset parameters. And again, we're just using uniform priors. So the value of the prior is just the width, 1 over the width of the prior for our uniform prior. And then we're going to set up our likelihood. Again, we're assuming that our data is Gaussian distributed with noise. Sigma equals 1. We can fit sigma as a free parameter, and you're going to see how to do that in the problem set after lunch. But for now, we're just going to assume that we know exactly what sigma is, and then we calculate our likelihoods on a grid, and then we calculate our posterior. So as a reminder, to calculate the evidence, first we're calculating the numerator of Bayes' theorem. Sorry. Just gonna write the Bayes' theorem back up so that we have it. In this case, we have two parameters that we want to fit. And we have our Gaussian likelihood of our data as a function of those two parameters. And then we have priors on those two parameters. And then we have our evidence for the sine model, which is just of data. Okay. So first we calculate our numerator of Bayes' theorem, and then we numerically integrate to calculate the denominator, the evidence, and then we normalize our posterior, and we can print out our evidence. We can see that this is a lot smaller than what we got for the line fit, and so this tells us that this is a really bad fit. To verify this, we can see what our corner plot looks like. For some reason, I can never get the corner plots to show up, so we can take a look at it. And you can see that this looks really weird, right? Like you basically can't see the posterior on this angular frequency parameter because it's railing right up against the edge of the posterior. So this tells us that we have made a bad prior choice. So we're going to talk about model misspecification again at the end, but this is a kind of model misspecification. We see that our posterior probability density on this angular frequency parameter is cut off. So what this tells us is that actually the true probability for this parameter lies to the left in the parameter space of what we've kind of arbitrarily set as the bounds of our prior. And so unless we have some really strong physical reason to believe that there should be no values of A below whatever I chose up here, 0.3, then we should choose a different prior on A and redo our analysis to eliminate this, what we call prior railing. So the fact that all the posterior density is pushed up against the edge of the prior tells us we need to pick a new prior. Okay, so we basically need to lower the lower edge of the prior. There was also a lot of the prior space where the likelihood was essentially 0, and so we can also lower the upper edge of the prior. So we're going to try to repeat our analysis, but this time we've hopefully chosen a more suitable range of priors for this angular frequency parameter. So we go through this process again, and we see that we have now calculated a much higher evidence. This is a good sign. Before we had chosen a bad prior, we got a low evidence because the allowed range of values of this angular frequency parameter did not provide a good fit to our data. We've now broadened our prior, and we can see that we've gotten a better fit for the data. We can verify this visually. So now we have a fully bounded posterior on this angular frequency parameter. There's no more prior railing, so we know we've chosen a good prior. Okay, so now we have calculated our evidence for this sinusoidal model. And so we can go back and calculate our Bayes factor to compare it against our original linear fit. But first, let's just do a visual check to see if our inferred best fit parameters for our sinusoidal model actually do a good job at capturing the signal in the data. And so towards the end, we'll talk about model misspecification, but I just want to stress that a lot of checks of model misspecification are visual, and you should not underestimate the power of just like plotting your results and seeing by eye, does this look like a good fit? And so as some proxy for the best fit parameters that we've inferred, we're going to take the maximum posterior. So we're just going to find the maximum posterior values of our angular frequency and offset, and then we're going to plot the sign model that those correspond to. And so you can see that based on our posteriors on A and C, we recover this green model. So it doesn't provide a terrible fit to the data. It's definitely better than that initial much higher frequency signal that I posited might fit the data at the very beginning. But you can see that it provides an inferior fit to the data compared to the true signal in the red line. And so we should expect that our Bayes factors are going to find a strong statistical preference for the linear model. Okay, and so we can calculate it, and we find that the linear model is preferred over the sign model with a log Bayes factor of 67. Again, this is working in log space, so this is a really, really significant statistical preference for our linear model. Okay, any questions before we go on to a slightly more complicated example? Yes.
Why exactly do we expect that this to be a representation of the goodness of
This is a great question. It's kind of yes. The question was, why do we expect the evidence to be a representation of the goodness of it? This is kind of a philosophical question. Basically, you can think of the evidence as you're kind of integrating your likelihood over the allowed prior volume that you've assumed based on the model you've chosen. And so if that integral is large, that means that the model you've chosen kind of like covers well the range of likelihoods for your problem. And yeah, basically you can think of it as like if this overall integral is large, then your the prior and the model that you've chosen provide good coverage for the data that you've specified. But again, this kind of goes back to, well, you can choose any arbitrary measure for goodness of fit depending on the subtleties of your problem. Okay. So this morning and yesterday, we were not always very careful about how we were normalizing our priors because we were basically only interested in posteriors. But when you calculate evidences, how you choose your prior matters a lot. So remember that the priors always have to be normalized probability distributions with respect to the parameters. The likelihood is not generally normalized with respect to these parameters. It's normalized with respect to the data. What it means to do an integral over all possible data realizations is kind of another philosophical question. But if you want to calculate evidences accurately, then how you choose your priors really matters. So let's take an example where we have some parameter and we've chosen some prior on it from x1 to x2, but our likelihood on this parameter is 0 over all regions outside this much narrower space. So if instead we had chosen a narrower prior that looked like this, our posterior would be exactly the same, right? Because the likelihood out here is 0. And so the posterior out here is also 0. But what about our evidence? So let's say this region is half as narrow as this region. How does the evidence change? Yeah, exactly. Exactly. So the value of your prior has doubled. So this has doubled. And so the value of your evidence integral, which is the integral of this numerator, is also going to double. So this tells us, one, that Bayes factors are a little bit arbitrary. So you have to take them with a grain of salt, right? You're getting identical posteriors for two different prior choices, but you're getting Bayes factors that differ by a factor of 2. And so are my prior choices for each of the two models that I'm comparing like well posed so that the comparison that I'm making is actually meaningful? And sometimes the prior has, like, in practice, very little of the factor that we calculate because it's going to be dominated by the likelihood. But sometimes it will make a difference, and we'll see an example of this in the problems. Okay, so far we've only been talking about Bayes factors, but in most real world situations, I
Or do you like do most of your work locally, so you need a beefy laptop, or?
Yeah.
Yeah.
So I cannot install updates. No.
I think it won't let me share because you're sharing, Adam.
These tables were really good.
Yeah.
No, that's, you know, wires.
Okay. Yeah, I'm almost connected. Can folks see the slides on Zoom now?
We see.
You're in the full bar of your browser.
Wow.
Oh, that was.
Yeah, I'll be a little bit. Can folks on this side still see it? Okay, cool. Okay, yes, so back to the question of bias. Apologies for the interruption. It's not a bias, right? You're encoding your prior beliefs, and when you report your evidences that you calculate with that prior, you're going to tell people what prior you used, and then they can get upset and divide the prior and apply their own prior. So it's not really a bias. It's like, it's a feature and not a bug of the Bayesian mindset. Okay, so one other example that I can think of is, for example, in a dynamical system. Oh, sorry, yeah, hand. Awesome. No, go ahead.
So radiation that might sine wave is your preferred model versus a linear effect, which would just be a long data.
Yeah, perfect. The other example that I was thinking of is also in my own research, but we generally assume that we are observing gravitational waves from circular binaries, but we can also observe gravitational waves from very eccentric binaries, like head-on collisions. And so we can calculate basically the probability of getting a head-on collision in a given dynamical environment, like a globular cluster. If you know the properties of the cluster, you can run an n-body simulation and basically calculate your prior odds of binaries at each eccentricity. Okay, so if we actually want to incorporate our prior beliefs in a specific theory, instead of calculating the Bayes factor, we can calculate the odds ratio. So in this case, hopefully you're all seeing the slides, the odds ratio is just the evidence for a specific model times our prior belief in that model divided by the same thing in the denominator. So, if you have some prior odds, you just multiply that by your Bayes factor and you get an odds ratio. Okay, so we've talked about the fact that Bayes factors are a little arbitrary. And so we're going to go through an example that is a really well-posed case where using a Bayes factor makes sense to distinguish goodness of fit. And this is in the case of nested models. So now we're going to go back to our linear data, and we're going to fit it with a quadratic function. So in theory, it should be equally well fit by a quadratic function as it is by a linear function, because a linear function is just a nested model within a quadratic function. And so if in the case we've now introduced a quadratic term with coefficient b, the linear model is just if you set b to 0. And so we're going to go through and we define a new quadratic model, And now we have a three-dimensional parameter space. So we choose our priors on our three parameters, the quadratic coefficient, the linear coefficient, and the offset. And then we're going to, again, calculate our data on a grid. Yes.
Very quickly, what is a nested model?
It just means that it is a subset of like a parent model. So the parent model reduces to the nested model in some limit. So again, an example from my own research, we can fit binary black holes and assume that the black holes have spin, or we can assume that the black holes are non-spinning. The non-spinning hypothesis is a sub-hypothesis of the spinning model where we've set the spins to a specific value in the parameter space. Another example, in the lambda CDM model, you can fix your value of H naught to what you've inferred from supernova cosmology and then have all the other parameters be free parameters, just as another example. Okay, so now we're going to calculate our likelihood on a three-dimensional grid, and I alluded to the curse of dimensionality yesterday. You'll notice that if you actually go and run this cell, it takes a little bit of time. You'll have to count to like 7 seconds or something, as opposed to yesterday where it just ran basically instantaneously. And so you'll notice that even with three parameters, maybe in this case you can wait 7 seconds, but you can imagine that if you were to add a fourth dimension, perhaps you would want to switch to a stochastic sampler instead of doing things on a four-dimensional grid. So again, we're going to calculate our posterior and our evidence. And we notice that our evidence is much closer to what we got for the original evidence for our linear fit. But now, in order to do an apples to apples comparison, we need to make sure that we're choosing our priors in a meaningful way. So we want our priors to be exactly the same for our nested models for the parameters that are common to both models in order for us to really get a meaningful base vector. But before we do that, we are going to take a look at our posteriors to see if they make sense. So you'll notice that our posterior on the quadratic coefficient peaks at 0, which is good. This is what we want for linear data. There should be no quadratic term that we find in our model. But again, there's some uncertainty because there's some noise in our data. Okay, so we're just going to go through and recalculate our evidence for the linear model using the same exact priors that we just used for the quadratic model on the M and C parameters. And so you see that we get slightly higher evidence for the linear model compared to the quadratic model. And if we compare the posteriors, we can also see that our posteriors on the M and C parameters for our linear model are narrower. So where is the extra uncertainty coming from in the quadratic model? Yeah, exactly. And crucially, the parameters are correlated with each other. And so you can get models that fit the data that look similar for slightly different values of M, B, and C. And so because these parameters are correlated with each other, when you introduce another degree of freedom, you get larger uncertainties in your two remaining degrees of freedom. But just to make sure that our results are sane, we're going to go back and basically look at the slice of our three-dimensional posterior where our quadratic term is exactly 0. And this should, if everything is going right, be exactly equal to the posterior that we got under the linear model. And so we've already calculated the full 3D posterior, so we don't need to go through and do it again. We can just find our 2D slice of our 3D posterior where B is exactly equal to 0. And then we plot that, and you can't actually see two sets of posteriors on this corner plot because they lie exactly on top of each other, which is what we wanted. Okay, so this was just to show what happens with your uncertainties when you increase the dimensionality of your problem. Okay, so finally, we can calculate our base vector, and we see that the linear model is preferred over the quadratic model with a Bayes factor of 3.16. So maybe this is not what we were expecting. So this is, again, a weak statistical preference. This isn't like whopping evidence for one model over another. But we kind of expected the quadratic model to provide an equally good fit to the data compared to the linear model. So why is the quadratic model slightly disfavored? So more complex models are generally going to be disfavored because of Occam's razor. So this is basically the principle that a model should be no more complicated than exactly needed to describe some data. And so a model that has more free parameters that aren't doing anything, that aren't actually needed to fit the data, are going to be disfavored compared to the simpler model by this Occam's factor. So let's look at a simpler example that's from one of the seminal papers in Bayesian Inference. So before computers, folks relied on mathematical tables in order to gain access to like values of numerical functions like sines or logarithms. However, copyright law only protects the expression of an idea and not the idea itself. So publishers of these tables had to come up with some way to prove that they have recomputed the values in the table themselves rather than copying it directly from an existing table. And so how did they do this? For values in the table ending in 5, they would choose randomly based on a specific pattern that they were going to encode into their table that only they knew, whether they were going to round that number up or down. And so if there were 2 tables that had the exact same rounding pattern, then you would know that the second table had been plagiarized from the first because the publisher of the second table should not know what rounding pattern the publisher of the first table had chosen. Okay, so let's take as an example, we have published a table that has 1,000 elements. And this means that 1 out of every 10 elements is going to end in 5. And so we'll have 100 elements for which we can choose the rounding pattern. This means that we can either round each element up or down. So the number of unique ways to round this particular table is just 2 to the 100, which is approximately 10 to the 3rd. So we were talking yesterday in the context of binomial distributions about combinations. This is just a permutation because now we care about the order in the table for each choice that we make. Okay, and so we have 2 hypotheses. The first hypothesis is that the table is plagiarized. Another table has come along and identically reproduced the rounding pattern of our table. The null hypothesis is that this table is plagiarized. The other hypothesis is that this is a random fluke. Okay, so now we can write our likelihoods. So the probability of observing the data, which is in this case, that the second table is identical to our table under the plagiarism hypothesis, is just exactly equal to 1, because if they're plagiarized, then the data in the tables should be identical. How about under the random fluke hypothesis? What is our prior probability, our likelihood that the data in the second table is exactly equal to the data in our table? 1 over? Yeah. It's just 1 over this. Yep. Okay. And so now we can calculate our posterior odds for each hypothesis. So we can start by calculating evidences. I'm going to move out of the way once I've finished writing so that folks on the other side can see. So for now, we can assume that maybe the 2 hypotheses are equally likely because we want to give the other publisher the benefit of the doubt. If we calculate this, we can factor out our priors and we get 1 plus 10 to the minus 30, which is basically equal to 0.5. So now if we go and calculate our posterior on the plagiarism hypothesis, we get 1 times 0.5 divided by 0.5. So this is basically 1. And our posterior on the random fluke hypothesis is going to be basically 10 to the minus 30. Okay, so we can see that the simpler hypothesis is much more strongly favored here compared to the complex hypothesis. So the simpler hypothesis makes one prediction that is exactly falsifiable, while the complex hypothesis is basically never falsifiable. And so this kind of demonstrates the power of the Occam factor, where in this kind of obvious case, we can see that the simpler model is all that's needed to explain our observation. And so it is very strongly statistically preferred. Okay, so we're finding this weak preference for the linear model, and we now understand that this is due to Occam's razor. So in many situations, redoing the analysis using the nested model is not always as computationally cheap as like running things on a 100 by 100 grid. And so sometimes we want to be able to calculate Bayes factors between nested models without having to redo the whole analysis. And we can do this using what's called the Savage-Dickey ratio. And it turns out that using the ratio of the posterior at the specific value of our parameter that corresponds to the nested hypothesis calculated under our full model divided by the prior on that parameter gives us the Bayes factor. And so again, to give a visual example of this, in the case of our quadratic analysis, I'm not going to draw it exactly right, but this is our quadratic coefficient. Let's assume we initially had some flat prior that looked like this, and we got some posterior on it that looks like this. Then the Savage-Dickey ratio is just the value of B in the posterior divided by the value of B in the prior. So this guy versus this guy. Okay, and so to check how this works, we can go back to our quadratic model. And unsurprisingly, it turns out that we get exactly the Bayes factor that we calculated by just repeating the full nested analysis and comparing it to our more complex model. So this is a really convenient way of calculating Bayes factors for nested hypotheses. Okay, great. Okay, so now we're going to move on. Yes.
More than two models.
Yeah, so then you would basically produce a matrix of Bayes factors. So the most preferred model is still going to be the one with the highest evidence. But then you would just like element-wise compare all of your models and you can like rank them in terms of which one provides the best fit. And they're not always going to be nested models, so you can't always use the shortcut. Okay. So in this case, we've been comparing two models or multiple models that we think might fit the data plausibly equally well. But sometimes we just want to check whether or not we've made a bad choice with a specific model that we've chosen to use. And so to do this, we can check for model misspecification. So there are several different ways that a model can be misspecified. So we already saw early on an example where we had misspecified our choice of prior. We saw that the posterior on our angular frequency parameter was railing, which told us that our prior did not cover the right range of the parameter space, and so we needed to choose a new prior. And again, we basically determined that visually. We plotted the posterior and we looked and we saw that it was railing, and then we tried out a new prior and we plotted the posterior again and we checked and we saw that it wasn't railing. So basically, many of these model misspecification checks are visual. Okay, we can also misspecify our noise model. So far we've been working with data that has Gaussian noise with unit variance. But as you'll see in the problems after lunch, not all data is going to be Gaussian distributed with unit variance. And so if you bake in some assumptions about the noise that turn out not to actually represent the noise properties of the instrument that you're using to make those observations, then you can still probably infer the right values of the parameters of your model, but technically you're going to be using the wrong likelihood to fit the data. And then in the case of the signal model, we saw a blatant example of this earlier where we simulated our data with a line, but we said, well, let's pretend we don't know that. We're going to fit it with the sine function. And so our choice of the signal model was misspecified. And so if we didn't know that we had simulated our data with a line, how could we test that we had misspecified the model when we assumed it was a sine? So there are many ways that you can visually check for model misspecification. In the rest of this lecture and then in the problems after lunch, we're just going to look at one example, but there are many other powerful, useful examples. I just wanted to give you kind of like one specific way that you can check this. So if the signal model provides a good fit to the data, then we expect the residuals between the data and the model to be Gaussian distributed, right? If we have some scatter about a line and we subtract out the best fit line that we infer, then the scatter that remains should just correspond to the noise model that we have assumed, which in this case is a Gaussian distribution with unit variance. And so what we can do to check this is we can plot the cumulative density function of the residuals that we calculate for the data and then compare it to the theoretical CDF that we expect. So in this case, the CDF of a unit Gaussian distribution. And we have some uncertainty in our measurement, so we don't just want to compare it to the best fit parameters that we infer. We want to check, like, given the uncertainties in our posterior, how Gaussian are the residuals for all possible values of the posterior that we infer. And so to do this, to avoid using a stochastic sampler, we're going to go through something called inverse transform sampling, which is just like super useful in general. So here it enables us to take a shortcut, but in general, it's very powerful because it allows you to sample from any one-dimensional distribution, and you don't need to be able to write down that distribution analytically. Okay, so we were talking about yesterday how CDFs are usually invertible because there's some kind of one-to-one mapping between the value of the CDF and the value of the parameter, where the CDF goes from 0 to 1. And so this means that we can calculate what value of the parameter corresponds to a specific CDF value by passing it through the inverse of the CDF, which, as we said yesterday, is the PPF, the percentage point function. So if we want to sample from the distribution corresponding to the CDF, we can take advantage of the inverse CDF. So we're going to sample randomly from a unit cube. And then for each of those random draws from 0 to 1, we're going to calculate the value of our parameter that corresponds to that value of the CDF. And this is naturally going to give us samples from the underlying distribution. And the reason that I say that you don't need to be able to write down the CDF or the inverse CDF or the PDF analytically is because we can use interpolation. So we've calculated our CDF numerically by calculating our posterior on a grid, the PDF, and then calculating the CDF using trapezoidal integration. And then we just interpolate our CDF or our inverse CDF, and that allows us to calculate basically the value of the parameter for any point between 0 and 1. And so in code, this is actually very simple and straightforward. So again, we're calculating our CDF using trapezoidal integration. We're drawing 5,000 random samples from the unit cube. So these are 5,000 points that are uniformly distributed between 0 and 1. And then we are mapping them using a simple interpolant where we're calculating the value of the parameter x at the unit cube samples. And what we're interpolating is the inverse CDF. So the value of x as a function of the CDF. You can imagine that we've rotated this plot by 90 degrees. Does this make sense? This is just like super useful, and basically any time that, for example, in nested sampling, as you'll learn later in the week, nested samplers draw points from the prior by doing inverse transform sampling in most cases. So if you ever want to use a nested sampler, you're going to have to implement inverse transform sampling for your prior parameters. Okay, so basically to show this in action, we can take our posterior on our slope parameter. The blue curve is what we actually calculated on a grid, and then we can plot our samples that we've generated with inverse transform sampling, and we can see that they agree. So this is just a histogram of the individual samples. Great, this worked. Okay, so now what we're going to do is we're going to calculate our residuals for the samples from the posterior distribution on the slope parameter that we just calculated. Okay, so to do this, we're going to basically take our posterior sample values of the slope. We're going to just fix the intercept to its true value for simplicity. And we calculate the expected value of the data given our linear model. And then we calculate the residual by just subtracting the model at this point in parameter space from our data. So does that make sense what the residual is? It's just the data minus the model. Okay, great. And then how do we calculate the data CDF? So we have a bunch of residuals. So now X is the residual. And our residuals are here. These are the individual values of the residuals. And so the CDF of our residual, we know it has to go from 0 to 1. And we have M data points. So we have M unique values of the residual. So then the CDF is just every time I encounter a new value of the residual, my value of the CDF increases by 1 on M until eventually it goes all the way up to 1. Okay? So this is the CDF of our data. What about the CDF of our model? Well, our model for our noise was to assume that it is Gaussian distributed with unit variance. And so now all we have to do is we use our handy SciPy function to calculate the CDF of a unit Gaussian. And where are we evaluating it? We're evaluating it at these X values. So we sort our residuals in increasing order, and then we calculate the value of the CDF of a unit Gaussian at these particular values so that we can compare it to the CDF that we calculated from our data. And so let's say that this line is now the model CDF. And if our model assumptions are a good fit to our data, these two things should just match each other, right? And so to see visually whether or not they match each other, we're just going to subtract the model CDF from the data CDF and plot it as a function of the data CDF. And this is what we get. So we've done this for many, many different draws from our posterior on the slope parameter. And we get this squiggly thing. So if the model provides a good fit to the data, then these squiggles should basically be symmetric about 0. And you'll see in the problems after lunch, or actually we might see in a few slides, what happens when basically the model is misspecified. So you'll see that this looks much more pathological. Okay, yeah, great. So now we're going to see what this looks like for our sinusoidal fit to our linear data. And so we would expect in this case that that CDF comparison plot is not going to be symmetric about 0. So we're going to do the same thing, except now we're fitting the sinusoidal model. So we are generating samples from this angular frequency parameter, and we make the same plot, and this is what we get. So we can see that systematically the model CDF and the data CDF are not matching each other, and the offset between them is always similar. It follows the same shape, regardless of which particular posterior sample we've drawn. So alone, one of these realizations looking like this is not necessarily a red flag because, again, we have some uncertainty. And so it might just be a random fluke. But the fact that all of them look like this is an indication of model misspecification. Okay, so that is the end. The point of this CDF plot was just to give you a flavor of one kind of visual tool that you can use to check if the model assumptions that you've made offer a good description to your data. But there are other things that you can plot, right? You can plot the CDFs themselves. You can plot the PDF of the residuals. There are many other kinds of tests that you can come up with to basically check if your model matches your data. That's just one example. So with that, we have time for any more questions. Yeah. Mhm.
in that case, how do you, is there a way to?
Yes, this is a great question, and I think you'll cover it later in the week. So there are basically two main methods for stochastic sampling. One is MCMC, which you guys worked on this morning. The other is nested sampling. So with MCMC, you generate samples directly from the posterior. That is your like byproduct of the algorithm, which means that it's not trivial to use an MCMC sampler to calculate the evidence. There are ways to do this. There's something called thermodynamic integration and parallel tempering, where you do some like temperature weighted combination of all the chains. But in general, if you want robust evidences, MCMC is not the way to go. In that case, you would want to use nested sampling, because basically what nested sampling does is it calculates the evidence and then you get the posterior as like a byproduct. The posterior is kind of your free lunch for calculating the evidence. And yeah, nested sampling works by basically reducing your full, whatever, n-dimensional parameter space, the integral over all those parameters, into a one-dimensional integral, which is really cool. So that's how we get evidences in practice for large dimensional problems. Yeah, good question. Other questions?
I see a lot of the stuff that people always like very frequently assume their noise is Gaussian distributed. I guess like is that like generally an assumption, or does it just kind of make it easier to interpolate, or like down?
Yeah, so this depends on your instrument and on the statistics of your measurements. So, for example, in X-ray astronomy, where you have like 3 photons for a measurement, you probably want to assume Poisson noise rather than Gaussian noise, because you don't have enough like samples to reach the range of validity of the assumptions of the central limit theorem. So in that case, you're going to have Poisson noise. In my field, we often assume that our noise is Gaussian distributed, but it's actually not. It's student T distributed. And so sometimes you can get away with the Gaussian approximation, and sometimes when you want to calculate evidences really, really precisely, you actually need to change your noise model and assume the right thing. So this depends basically exclusively on the properties of the instrument that you're using to make the measurement. Yeah.
Solution. So notion otherwise.
Great. All right. If there are no other questions, we've reached lunchtime. Thanks, and apologies for the weird technical issues.